In this video, I'm going to show you how to simplify cube roots by doing the following two problems. To simplify a cube root, I'm going to use the following property. The property of nth roots. We know the nth root of AB is equal to the nth root of A times the nth root of B. Or it also works that so anytime you have the multiple of two things, you can split it up for any nth root. Square root, cube root, fourth root. The nth root of A over B is the nth root of A over the nth root of B. So you can do it for multiplication or you can do it for addition. By the way, it does not work for addition and subtraction. Let me show you some examples on that. Let's look at the square root of 36. You know that's 6. But if I think of square root of 36 a different way, that would be the multiplication of two perfect squares, 4 times 9. And I can split it up using this nth root property. So we know that that is equal to 2 times 3, right? Square root of 4 is 2, square root of 9 is 3. That is also equal to 6. So you can see that it does work. Let me show you where it doesn't work for addition. So let's do the following example. Let's do 9 plus 16, because we know that that would be the square root of 25. Because of the imaginary parentheses, we know is 5. But if we split this up and think that it would work, this property work for addition, well, you're going to see it's not, because the square root of 9 is 3 and the square root of 16 is 4, and that's 7. And these two are not equal to each other. So you can see it works for multiplication, but it doesn't work for addition or subtraction. And multiplication it does. Okay, so let's go ahead and use this property for the first one. So now, but the second thing to notice is they did ask to simplify. If they said to evaluate or to estimate, I would just put that in a calculator and get a decimal approximation of what the cube root of 448 is approximately. There is a decimal approximation that would work. But they're not. They're asking us to simplify. So when they ask you to simplify in any nth root, what they want is you to take out anything that's perfect. So we're looking for perfect factors in 448, which I know might be a little challenging because that's such a large number. So let's go ahead and do that work over here. I'm just going to find factors of 448. You can, 4 I see as a factor. I'm just going to make a tree. And then that would be 1, 1, 2. You could have just said 2 as you will. Let me see. I don't know what else. Let's go for 2. What would that be? That would be a 56 if you divide 2 into 112. And 56 we know is 7 and 8. And I'm going to think of what are my perfect cubes. I know cube root of 1, that's not going to help us, is 1. But the cube root of 8 we know is 2. The cube root of 27, for instance, if there was a 27 in here, that would be perfect. So we're looking for one of these perfect cubes in this factor. I'm going to put a square around that because that's extra. So that's what we're looking for. So I'm going to come around here and I'm going to say, okay, the cube root of 448. That's the same as what perfect thing? I know that 8 is perfect. There's another 8 that is perfect here. 4 times 2. That makes an 8. So we use that one. And there's a 7 left. The cube root. So we can now use that first property and say this is the cube root of 8. Split it up, because it's all multiplication. Cube root of 8 again, multiply 2. And then a cube root of 7. But we just saw that the cube root of 8 is 2. So we have 2 times another 2 times cube root of 7. So what would that be? That would be 4 cube root of 7. You could have done it a more sophisticated way and realized that the cube root of 64 is 4. Let me go ahead and erase what we have here. Oops, that's not erasing. And we could have realized that if 64 did go into, no, or maybe 7. 7 into 448, we realized is 64. So if you originally found 64 as your answer, as a factor, and you wanted to go straight for that, that would have worked as well. That's 64 times 7, cube root of 64 times cube root of 7 using our property, and cube root of 64 is 4 cube root of 7. So that's if you saw that 64 was a perfect cube. A lot of people, what they do is they just divide each one. Does 8 go into it? It does. But then does 27 go into it? Does 64 go into it? And then they try to find the largest one that goes into it if you want to use that second method. Otherwise, you could just make a tree. So if I do the more sophisticated way on this, right, 27 times 2, sorry, times 3, is 81. So I know that 27 is a perfect cube, and it goes into 81. So that is what I'm going to do. I'm going to make this a 27, we have a negative, times 3. Okay, what is a perfect cubed in x cubed? Well, the cube root of x cubed is x. I know that. So that could be an x cubed times, there's 1 left over, x. Okay, let's keep on going. What about a y? Well, you could do y cubed times y cubed, the unsophisticated way, and then that would be 6 of them. There's 2 left over. Or, let me erase this. We could realize that anything that has a division of 3, like y to the 6th, that is going to be y squared, because y squared times y squared times y squared is y to the 6th. So we know that the exponents have to be divisible by 3. So what would that be? That would be y to the 6th times y squared is another 2 factors to make a tree, or whatever, have you have it, of y to the 8th. So now we have not changed the problem. This is an 81, this is an x to the 4th, and this is a y to the 8th. So let's just write all the perfect things first. Negative 27 on the left, x cubed and y to the 6th. Those are all the perfect things. The things were not perfect is x, oh, I forgot the 3, a 3, an x, and a y squared. Okay, now I'm going to use my cube root property. Let me scroll down a little bit. And I know that this is the cube root of the first clunk of stuff times, and you could even do it separately if you wanted. So right now we know that cube root of 27 is negative 3. The cube root of x cubed is x, and the cube root of y to the 6 is y squared. Those are all the things that were perfect. So then these guys are not perfect, so they cannot come out of the radical. So that would be my answer. And my first one, that was my answer. Hope that helps.